Today we're looking at a electricity problem. So 2552 here, an overhead transmission cable for electrical power is 2000 meters long and consists of two parallel copper wires, each encased in insulating material. So we develop a short circuit somewhere along the length of the cable where the insulation is worn away and the two wires come into contact. So the idea here is you work for the power company and you have to locate the short so the repair crew can be sent to the location. So it's 2000 meters long. So maybe it's going to be difficult enough to pinpoint where it happens. So both ends of the cable have been disconnected from the power grid, and you have at one end of the cable connected the two wires to a 9-volt battery that has a negligible resistance inside the battery, and you measure 2.86 amps of current through that battery. At the other end of the cable, then you attach the same battery to those two wires and you measure 1.65 amps of current flowing through the battery. So, how far is your short from point A? Now, the absolute first thing you have to do here is to draw a diagram and sort of give yourself a visual picture of what's going on. So we started with our two wires. Whoops, doesn't matter that they're not particularly straight. So let's say we've got two wires that look something like this. Now, they're a short, so this is how the wires would be how the wires would look in normal operation. And this is our point A and this is our point B. So the problem now tells us that we've developed a short circuit somewhere along the wire. So let's imagine now that wire, okay, let's call this wire 1 and wire 2. So these guys have somehow joined together at some point. Now, it doesn't really matter where we draw our short, something like this is fine. So these two wires now are all of a sudden joined. So the idea now is that if you put, for example, let's say you take your 9-volt battery and you put it across here. So this is your 9 volts. We'll draw in the symbol for a battery. Now the circuit that you're drawing, let's just sort of trace it out in red here, is going to be this path here. So you're measuring basically the current along the part that I've drawn in a dashed red line. When you do the same then at point B, you're measuring a similar circuit. And what you can see is that depending on the path that the current takes, you're going to be able to, or the question is asking us to figure out how long is that length of wire. So what we know, from our studies of electrical currents and resistance is that the resistance of a piece of wire is the resistivity is of the material it's made from times the length of wire it travels through divided by the cross-sectional area of the wire. And it's a metal wire, so it's going to obey Ohm's law. So V is going to be equal to I times R within the wire. So let's call this distance here X. So there's a certain distance between point A and where the short circuit has occurred. And then what that's going to tell us is that the distance from B to the point where the short circuit has occurred, I'm not sure what happened there, is going to be a distance 2000 minus X. Because if the entire wire is 2000 meters long and the distance from A to the discontinuity, the short circuit is X, then it follows that the distance between B and the short circuit has to be 2000 minus X. So how do we set that up now to solve the problem? Well, the way we do it is we realize, or we make the realization that V, the voltage of our battery, is going to be 9 volts in both cases. So if the voltage in both cases is the same, and we can then use Ohm's law to make the equivalence that V is equal to R1 times I1. So this is going to be our circuit 1 here, if you like, and this is going to be our circuit 2. So the voltage is the same in both of them, which means the product of R and I is going to be the same in both of them. So it's going to equal R2 times I2. Now, we're going to we've called the distance from point A to the short circuit X, so that's fine. So what does that mean for our resistivity? Well, the current has to take a round trip, so it's going to take a round trip from the point where it starts through a distance of X, and then ignoring sort of this cross part here, it's going to travel X again to get back to the other lead of our voltage source. So the resistivity, R1, we can write in terms of the resistivity is going to be equal to the resistivity times 2x. So 2x is the length that the current has to travel through to get from the positive of the power source back to the negative of the power source. So we divide that then, as per our resistivity formula, by A. So we know that's what R1 is. What's R2? R2 is going to be equal to the resistivity again times 2, because it's traveling twice this path length, and our path length here is 2000 minus x. So to get from point B to the short circuit here and back again is a distance 2 times 2000 minus x. So now we have the problem set up. We can just plug in the numbers by combine those two equations and plug in the numbers, and that should solve the problem for us. So let's do that then. So now what we have is that rho times 2x over A times I1. So this is what we have here. Oops, I've drawn that slightly wrong. Let me start that again. Oops. Sorry about that. Now, sorry, try that one once more. So we've got rho times 2x over A times I1. So this is these guys are equivalent here where I'm drawing the arrow. So that's one equation for what's going on in loop 1, if you like. And then in loop 2, we've got rho times 2x. Sorry, 2 times 2000 minus x. Sorry, I'm getting confused here. Because that's our distance of interest from B to the short circuit. And that's I1, that's I2, and this guy is going to be divided by A2. So now the 2's are going to cancel, and the A's are going to cancel here, and we're going to be left with 2.86 amps. And sorry, the rows are also going to cancel. So we're going to be left with 2.86 amps, which is our current in circuit 1 times X, and that's going to be equal to 1.65 amps, which is our current in the other circuit, if you like, times 2000 meters minus X. So that's after we cancel everything out and put in the currents that we know. This is the equation that we get, and that's a fairly easy it's a fairly easy calculation then to solve for X, and we get X equals 732 meters. So our short circuit, I keep calling that a discontinuity, it's the opposite. Our short circuit is 732 meters between A and B. So my initial stab at drawing the short circuit in the right place looks like it was reasonably successful. So now we're able to tell the repair team, based on our diagnostic measurement of the current, that they should go to a point 732 meters down the cable, and that's where they should find the short circuit, and that's where they should carry out the repair.